All right, here we go. Deals with quantum mechanics, which you will love and adore in physical chemistry next year. Oops, why did I write it like that? So IR, which is infrared, has to do with molecular vibrations. Ranging from sigma to pi to double pi bonds and such. If it's just say it's just like a monatomic helium atom, without a bond, without a hybridized bond, we really cannot observe IR. So the way to think about it is we've got, say, like atom A connected to atom B via a spring, and depending on how tightly we pull that string or how much energy we pulse it with, that's going to be its vibration. So again, remember that there's an inverse relationship between energy levels and wavelength. I should mention this first. What's really important about this is the theory of quantum. Well, it's really the whole basis of quantum mechanics, is that electrons can only move in certain steps. And that makes sense because we've seen orbitals like 2s, 2p, like sp3. It can only move down from one orbital to the next or from one energy level to the next. And it has to have the right amount of energy. Needs right amount of energy. If it's just a little, even if it's just a little bit off, it cannot be like 10 to the negative 15th with a absolute error of like less than 0% or very close to 0%. It has to be the exact. Otherwise, it doesn't react. So that's why IR and NMR are both very useful analytical tools, because we know that when we read it, something is there. So IR has to do with molecular vibrations. NMR, which stands for nuclear magnetic resonance. Resonance. That's really all just about where we've got a nucleus, we've got a magnetic field, and we observe the spin of the nucleus. And the most common one is, well, what do you know? It's going to be one hydrogen, because that's only got one proton in it, and it's easy to observe one proton instead of like 15 or 16. Now there is carbon-13 NMR, but we really haven't gone into that so much, so don't worry about that too much. If you want to get rid of your NMR, so say you're synthesizing a product, and you start with, say, methanol, and you want to go to like acetic acid, and you're asked to record the NMR species of it. The quick and dirty way to avoid having to do NMR or proton NMR species is just to replace all the protons with deuterium, and you're good to go. It will only read one hydrogen. It won't read deuterium or any other isotope of hydrogen. So that's why it's important. And now looking at the general trends of the IRs, remembering that there's the inverse relationship between the wavelength and the energy level, you see that the higher the wavelength, Let's see, I'll draw this down. Oh, it's not quite. It's not quite that trend as it shows here. What was I trying to say with this? So this one has a low wavelength, but a high energy. And that makes sense because we're attached to two very electronegative atoms. Versus if we compare it with the triple bond, that's way more rigid than is a single sigma bond. So that definitely has lower energy, but a higher wavelength. And so whenever we're talking about IR, what these different words mean, weak, medium, and strong. So I'll just draw a graph right here. So it's typically, let's see, it's usually, why they do it in inverse centimeters, I don't know. It's probably just to make things standardized. But by weak, we mean, so let's say this is like, what are the units on the y-axis? I don't care. What? So if it's weak, it's so this is just to give you a relative idea, so you're not confusing the signals. Because if you look, there's a lot of overlap between these numbers, and these numbers are accurate enough that say you observe like a cyanide group in there, you'll be within that range. But that still does overlap with other things. Hence the reason why we need the relative intensity. So weak intensity is like, whoop. Medium is somewhat like this. And strong means it basically touches the bottom of the graph. So that is a helpful distinction for you when you're doing an IR problem. And also really good, the first thing you really want to look for in any IR problem is the carbonyl group. That is like, thank you, Lord, for sparing me today. That is, whenever you see 1700, it should be like, oh. So look for that. And then broad versus very broad is just how wide it is. And so with that in mind, I have a couple of problems that I pulled out from the textbook that we can work on. Let me see if I can remember what they are. What? I went through with someone else and said like, ooh, that looks like a nice problem. These are the best problems that I can find that best represent like what he's talking about during class. Actually, does anyone have their book with them? I'm going to borrow yours. So the problems that I would recommend doing for NMR at least are 54 NMR practice. Do 54, 66. Wait, no, that wasn't the one. Was it? Yes, it was. 54, 66. I guess 73 would be a good one too, but whatever. That's 72. 80 and 82. These are the problems, especially 82, that I would recommend working through in order to get a better gauge of where you're at. So going to 54, because I've already done these with a couple people and I don't want to penalize them for being here, so I'll do the other ones that I have not yet done. So looking at 54, no, that one's actually really easy. I'll do one that I didn't get. I wouldn't imagine it being on the test, but it'll prepare you well enough to get these other ones done. So looking at 73, the following spectrum appears in an old catalog of proton NMR spectra of organic compounds. This is problem 73. Is the assignment structure correct? What's wrong with the assignment? So this looks like benzene ring with carbonyl. With alkene, carbonyl, two hydrogens, and the spectrum looks like this, where its chemical shift, oh no, I want to put that a little bit lower. And so at 7 and 8, 7, 8, and this is ppm, we've got like a peak right here and a peak right here with a little bit of splitting, but not much. At about 5.5, we have a, looks like a quartet, and that tells us it's one hydrogen. And for the other one, it looks like we have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. I'm just going to write 8 and say good enough. And then, of course, we have 0 ppm. So so you know, the peaks, or rather the height of the peaks, really means absolutely nothing. The important thing under here is the integration term. And I don't think, do you want me to go over that a little bit right now? So you might be thinking, when am I ever going to use calculus in chemistry? Well, here you go. We just throw it into the computer and say, whatevs. So let me do something different over here. So say we had something like this. I'm just making this up as we go along. So when we integrate it, say this is like 5, this is like 1.5, and then this is 6. Whenever you do the integration for the NMR, it's referring to the lowest ratio of protons possible. So if we do like 6, so if we look at 1.5, obviously we can't have 1.5 protons. So what we have to do is take the ratio of them to each other. So we go 6 to 5 to 1.5. So 6 divided by 1.5 is like 9. 9. This is 7.5? Yeah. And then this is 3. But then we have to multiply it by another factor in order to get whole numbers. So if we get a ratio that has fractions in it, we basically have to multiply them all by a common factor, so they're all whole numbers. I don't think he'll do that to you, but that's still that's just good to be aware of. Oh, whoops, I meant to divide by 1.5. Like so. Oh, you're right. 4. Oh, that's a good idea. What's 5 divided by 1.5? It's like 3.5? No, it's like 2.5. You get the point I'm trying to make, right? What? Yeah. And remember, be careful that this is the lowest ratio possible. Unless the diagram specifically says, like, we know how many protons are in this environment, then go off the lowest ratio. In this case, for this particular problem, 73, we're given that at 3.5 we have 2 hydrogens, and we have 1 hydrogen right here. But we've got to look, if we know what the compound looks like, it's a good idea to first assign groups. Assign groups according to signals. So what we've got here is like we've got 2 protons that are, This is where the point is. And this molecule, we're only going to count this side, and this side is the same thing. Why? Because it's symmetrical on the so we can just, so this will definitely cause the splitting that we'll see down here. But we only have to count this one. But back to what I was saying. So this hydrogen is attached to an alkene. So let's figure out what that shift is. So going back to these beautiful charts. So this is proton NMR. So let's see, we have hydrogen. And by the way, if you have something that's like not quite, so like in this example, it's really H and then attached to another R group. This is still valid enough for the purposes of the question because it's more qualitative than quantitative. So we should see something around 4.7. This one actually extends all the way up to 4. Wait. Did it say 4.7? Oh, yes it did. Oh, it does make a difference. And we have it right there. This one's actually going to be a little bit higher because, oh, man, I am not doing well today. I am trying to look at this one in the middle, where it's attached to an alkene attached to a carbonyl group. That shift should be pretty high then. Where's the ketone group? We'll just say it's this for now. That's close enough. Yeah, you're right. So we've got the 5.3, and fortunately for us, we see something at about 5.5. If you look at the problem, it is about 5.3. So so this hydrogen I'll label as HA. So here's HA. Uh-oh. What's the problem there? That, yes. So just by looking at that, we see that this is not a valid NMR for this species. Why? Let's look at it in more depth. So according to the N+1 rule, this should have 1, 2, 3. It should have 3 neighbors. And whenever we say neighbors, we mean they are non-equivalent protons. So comparing these two hydrogens in blue, they will not cause each other to split. And furthermore, because it doesn't have 3 neighbors, it actually has, well, none. We should observe just a singlet, like that. And the other thing that should tip you off right away is it tells us we should experience 1 proton right there. Whereas in fact, we actually experience 2. So that's what? Yeah. Mm-hmm. Mm-hmm. No, it shouldn't. It says would hydrogen have 2? Yes, Tyson? Sure. So by neighbors, the general definition is we are 3 sigma bonds away. So we'll take something like this. So here's hydrogen, hydrogen. Those are not neighbors because they're attached to the same carbon. These ones over here, 1, 2, 3, 4, they're too far apart, so those aren't neighbors, but these two sections right here, those would be neighbors. Yep. If we're considering these two, yes. Let's just make this a hydrogen to make it. No, they count as 3 neighbors. So if we're looking at these ones right here, so if we're looking at the hydrogens on the end, we only look at the adjacent carbon. Now, to explain it in terms of the explaining in terms of the double bond, so we've got to add in something like that. So we have H, H, H. What's special about the double bond that is present in the single bonded structure is that we've got rotation here and none over here. So these hydrogens on the end, so even though they're one, let's do a different color. 1, 2, 3, 4, 5 away, they're still close enough to interact with the hydrogens over here that they can cause splitting. That's not something, that's really more advanced material. Just go with like on adjacent carbon, 3 sigma bonds away, that's what causes splitting. If they are equivalent, I'll just write this down. Sure. So equivalent proton environments do not split each other. They will just cause the area under the curve to be larger. So looking at propane as an example, I'll label these HB, HB, HA, HA, A, HC, HC, HC. What's wrong with that picture? Yep, A should be C. Yes, so looking at so HB, how many neighbors does it have? 1, 2, 3, 4, 5, 6. Yep, it has 6, so it's going to do an n+1 splitting. So we should get a septet, whatever we call it. Oh. So if they're equivalent to each other, so HB will not cause HB to split. HA will not split HA. HC will not split HA. Yeah, then that would make a difference. So like going back to this example, these were both, we could pretend like they're HA and HB, they're still equivalent because of symmetry down the middle. HA will not split HB. HB will not split HA because they're the same. Whereas here, HB is different from HC and HA. So HA and HC will split HB same. NMR is actually a really advanced topic, and I'm surprised we're even like talking about it. I guess he loves chemistry too much. But this is really if you're an analytical chemist, this is the kind of stuff you'll be doing all day, just staring at IRs, NMRs, and be like, what am I doing with my life? Which is why we just get computers to do the hard work for us. Does that make sense, the splitting pattern for propane? Okay. In fact, do you guys want a strategy of how to like attack the NMR problem? Here is the strategy that I would suggest. And does anyone know how to make this keyboard thing push in? being stubborn with me. There are no buttons. Oh, wait. Oh, there we go. Okay, who was that? Dyson. Okay, you get +5. Not really, but... Well, I'm already giving everyone, like, +5. Well, Jeff is giving 1, but I'm giving. So, who's the better one? So, NMR strategy. Or we should include IR in this. IR and NMR strategy. So you get your list of compounds, whatever they might be, derive expected signals. So like if we have a carbonyl group, we say, okay, well, we should expect something around 1700 inverse centimeters. And for this NMR, we've got only one proton environment. Well, that's the second step. Determine number and splitting of proton environments. So that's on the IR, and then on the NMR, oh wait, this one still has a signal on the IR too. What is it? IR. It's a CH bond. So I'm going to say we're going to expect something around 3000. Most typically, a lot of these values that you'll observe are right in the middle. So it's safe to take as an initial estimate just the average. So like these two in purple, we just say, okay, we can guess 1100 or something. Yeah, when it's IR, it's usually pretty clean what it looks like. The peak is, you might get like some noise in there like that, but the peaks, there's no splitting in IR. That's what you're asking. Yeah. So, and the intensity of it has to do with the strength of the vibration itself. But that doesn't have to, the intensity, like how tall or how wide the IR band is, has nothing to do with how many bonds are experiencing it. So this one, we looked at that. So CH, this is just acetone, which is a pretty simple example. That's about 3000 inverse centimeters on the IR. And fortunately for this one, we see on the NMR, we've only got, well, now we're on the second problem. Determine number and splitting of proton environments. So we've only got the HA, 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 HA. And in fact, when you're going through the list of compounds, I would in fact label as like HA, HB, HC, H alpha, beta, whatever. You can name a molecule after me if you want. So you go HG, HA, HB. Maybe there will be 7 proton environments, which would be interesting. Conceited. So we've determined, okay, so there's only one environment. But what's the splitting pattern of this guy? Well, I mean, like, how many peaks are we going to observe if we were to look at it? In NMR. Yep, it would just be singlet. A really big singlet. Because here we observe it's 1, 2, 3, 4 away. And it's not the case with the double bond we saw earlier, where they were both on the same side, and we could access each other pretty easily. Here they're on opposite sides of the double bond, which is why we cannot access them. So we get one singlet, and yeah, 6H via the integration is what we should see. And so do that for each molecule, and then it's just a long process of elimination. Well, it's gonna be a taller peak on the NMR because more protons are there. Oh, on this one? No, I'm just doing this in isolation. So yeah, we have to. So that's why problem number 82 is an especially good one to work through. Let's do it. Do you guys want to do number 82? Okay.
So for this problem, just ignore for the purposes of this test, ignore the fact, well, someone asked about the force splitting pattern, where the double bonds are, say, 4 sigma bonds away, 1, 2, 3, 4. For the purpose of this test, just say the neighbors are protons that are 3 sigma bonds apart. And that's where I got stuck with this question, because I thought that 4 rule applied, but it really doesn't. So just go with 3.
Okay. Now I'm going to do is I'm going to take a picture of this page really quick so everyone can see, because not everyone has a book. Now why buy the book? Because we never actually used it. So here we only have the proton NMR. What I should say about IR first is use IR to determine your functional groups. And use NMR to determine the shape of the molecule. Not like its 3D molecular shape, but its connectivity space. Okay, here we go. So we've only got NMR, so let's identify the number of proton environments we have in each one. And just so we keep it uniform, let's do it in... Orange is a little bit more readable on this. Is it? No. I want to do each one in a different color. Green? Okay, I'll do this first one in green. So let's count the hydrogens. 1, 2, 3. So in that one we have three different proton environments. They are not symmetrical in this case. Can anyone else tell me why? Or why they're not the same? Yeah. And so in B, the case is actually different because these two hydrogens are the same. So these both count as one environment. And of course we have this H up here, so we should expect 2 peaks from that graph. This one, we have H, H, and then H again. Those aren't equivalent. We've got 3. Here we've also got 3. H, 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 3. So it looks like the one that should be the easiest to identify is letter B. We should only see 2 peaks right there. And what's also very special about this one is that we have no splitting occurring. Why is that? Well, we're too far away. 1, 2, 3, 4, 5 bonds away in 1, 2, 3, 4. That's still 4 away. In either case, we're 4 or 5 away, so we should see no splitting right there. Then analyzing the splitting pattern for the rest of these, we should also see no splitting here. You might be asking, well, what about these two hydrogens right here? Well, they are too far apart because it's 1, 2, 3, 0, 4. Oh, yeah, that does count. Never mind. So, yes.
No, it doesn't.
So apparently with sigma bonds, with pi
Then this guy is going to want to, this guy's going to keep it. Like, imagine if you have a nail right here, right? Then that's going to keep it. But
bonds, we can be 4 apart versus sigma. If it's just all complete with sigma, it's just. So this one should have splitting because it is 4. Yeah, because it's 1, 2, 3, 4. Oh, sorry. Oh, whew. Good thing I'm smart. Whatever. Good thing I have smart students. Good thing you guys are chemical engineers. Then this one, so 1, 2, 3, 4. 1, 2, 3, 4. So those should be able to split each other. And they're not equivalent. So this guy has 2 neighbors. This hydrogen and this hydrogen. So we should expect a triplet. N plus 1, 2 plus 1 equals 3. Yeah. Because we look at this hydrogen, it's 1, 2, 3, 4 away with the pi bond. And same with the oxygen one, it's 1, 2, 3, 4. Oh, I'll draw it out like this. So you can see it's 1, 2, 3, 4 bonds away. Yeah? Mm-hmm. We'll just go with that. Yeah, 3 would count as well, for sure. Yeah. So if we had like a hydrogen right here, instead of it attached to another R group, that would cause splitting. That goes into, this gets into some really deep philosophical and quite scary illusions. My organic chemistry class required me to read like a whole NMR textbook, and I was like, please no. So, well, it wasn't required, but it's like, oh, you get this on the test, and it might be a test question. So it's like, okay, so for this one, we expect a triplet. And for both of those, the OH and the H, we should get a doublet, because they each have 1 neighbor. Okay. And then this one here, it's got 2 neighbors again, so we say it's going to be a triplet. And then this one is a doublet. And then this one is a doublet. So now I've identified the splitting patterns and what it should look like. I'm not going to do it here because there's really only 2 types of signals we can expect, which is from the benzylic hydrogen and the OH. But definitely on the exam, go through and just label numbers to them if we have like, say 4 or 5 different environments. So let's go through each of these and figure out which one best matches. So part A. So it looks like we have 2 peaks. Oh. Are those splitting? So that means B has to go with number 1. I think that's right. Yep, so B gives us no splitting. Because those are equivalent. If we were to make this a carbon instead, then we'd get some splitting. But we'd have a different environment too. So now we look at number 2. Oh, this is a mess. Wait, no, this is not number 2. This is number 2. So with number 2, it looks like we have 1, 2, 3 different environments. And this one, so when we're talking about splitting, they basically have to be right next to each other. So it's like, so if this were a split, they would be like, kind of like a violin string where you can. No, that's not a good analogy. Yeah, so like here, right here, this is splitting in one environment because they're so just nestled on top of each other. Actually, that one, no. But so here we expect 3 environments, or really they could be the same environment. 3, 3, 3. Doesn't look like we have any. Oh, yes we do. Hello? Okay. The Clyde building? McDonald? Oh, the McDonald. I thought you meant the restaurant. Yeah, I know. Yeah, it does. That's good enough. I'll be done in about 10 minutes. Actually, it might take me like 20, but I'll call you when I'm done. I'll be about done. Get a haircut. McDonald. Well, meet at the McDonald's. Bye. Bye. Sorry for the pause. Here we have the doublet because they're right next to each other. No, that can't be right. So this is where I was talking about earlier. Here they're actually too far apart from each other because it's 1, 2, 1, 2, 3, 4. It's 4 sigma bonds. So this one, wait. Ignore what I just said. Just. No, it won't. Yeah, that's right. Yeah, so this one doesn't have any splitting associated with it. We're looking at 1, 2, 3, 4, 5. Yeah, that's 5. And this one's only 4. 1, 2, 3, 4. Honestly, I want to say this one doesn't cause splitting. Yeah, so that would give it 3 different proton environments without the splitting. So this one, I believe, is. Most likely. You know, I'm just going to say, like, ignore the 4-way rule and just go with 3 sigma bonds. Forget that, whatever. Don't forget it, but for the purposes of this test, don't worry about it. So in other words, forget it. So yeah, we'll say that this one does not cause splitting. Oh, you know what I think it is? It's because this is a benzene ring versus just a normal normal double bond. Yeah, he's not. Which is why this is a good problem to do, because it's really... Okay, let's look at 3. Actually, let's look at 4 because that looks a lot nicer. So 4 looks like, again, we have 3 environments. Yeah. Oh, okay. Let's just finish this problem because we're almost there. Yeah, I get what you're saying. NMR is... The theory is straightforward, but there are so many little exceptions to the different rules that people have written books and libraries on this topic and have dedicated their lives, for who knows what reason, to studying this topic. Friedel Crafts, the guy who came, the one that reaction we've done. No, it's like Mick Lafferty arrangement. Yes, it was his textbook that we had to read. Mick Lafferty, he's like, flatteringly, this is referred to as da-da-da-da-da. He's like, haha, I don't know what I'm doing. Alright, but aside from the point, so it looks like right here, in both of these cases, we've got doublets, and then just a singlet here. Let's see what that matches up with. This one we pretended was not there because it's too far away. Yeah, sorry, this one would be the one with the doublet. Yeah. And is that what we observed below? You're welcome. Bye. We get singlet, doublet, doublet, so 4 probably has to be D. And then by process of elimination, 3 has got to be C. That was a good problem. Because we've got, so both hydrogens, this one does not have It just means it's like really close together. So like here with 7, you see that they're, so comparing 7 with, number 2 with number 4, you see that there's a better resolution. Here's just smashed. I do not know what that is. Yeah. Alright. But this should be enough to get you gauged for being able to tackle the problem. So you should... This is probably going to take you the longest amount of time, but it should be easier than this. Alright. I think we're good.